Hello, calculus. I'm back for part 2 on 6.1. Okay, so when we left yesterday, we had done an LRAM and an RRAM. A couple of things to note as I start this one. For the LRAM, we used these values here for the heights of our rectangles. So, for example, here this first rectangle was 1 by 2. This next rectangle was 1 by 3. So on and so forth. This one was 1 by 6, and this one was 1 by 11. And then for the right we used these. So when you have a T-table, it's really easy to do a left and a right. You're just going to pick up the first, second, third, and fourth heights for this particular problem. And for the right, you're going to do the second, third, fourth, and fifth. So you need 5 total if you're going to have 4 subintervals. So the blue here were your left heights, and over here were the right. And then I want to make a clarification. When I was down here just trying to write this exact number here, I used an initial value of 0.2. That's actually inaccurate. That was the initial velocity. So if we were doing this problem here with antiderivatives, and we went t cubed over 3 plus 2t plus c, we aren't giving this, we need the initial position. And so they didn't give us an initial position, so we're just going to assume that s sub 0 initial position is 0. So I actually was just off script there and threw in 0.2, but that's the initial velocity, not the initial position. So we're just going to use a c equal to 0 here. Okay, and so then you would see that this s of 0, or sorry, we're doing what after 4 seconds? The s of 4 here, the s of 4 here actually computes to be, if you put it into this, if we put it into this antiderivative, 64 over 3 plus 8, it comes out to 29.3. So if the initial position was 0, this is 29.3 feet. That's your most precise answer, assuming an initial position of 0, 0. So that is certainly between 22 and 38. And then we're going to do a midpoint today, and you're going to see that it's really close to this. And another thing you could use to approximate also is to add the left, to get a little bit more precise, add the right and divide by 2, which gets you 60 over 2, which is 30. So 30 feet is looking pretty good, as you can see, assuming initial position. This is 29.33. But let's see what our new method turns out to give on the next page. Okay, so the next method is going to be a midpoint approximation. Okay, so this is the next 2 pages here, midpoint approximation. So the midpoint here of this subinterval from 0 to 1 is x at 1/2. So this time, instead of drawing triangles from the left or from the right, I'm going to draw them, rectangles from the left or from the right, I'm going to draw them from the midpoints. So 3 over 2, 5 over 2, and 7 over 2. Okay? So let's see, let's graph those points. We had 0, 2, we had 1, 3, we had 2 was at 6, we had 3 was at 11, and we had 4 was at 18. Okay, here's that. There's the area under the curve. And now I'm going to draw these from the midpoint, the heights from the midpoint. So not on the left, not on the right. I'm going to go to this midpoint. Okay, and so what you do is just create a T over, like a T over the width of the subinterval. So like that, and like that, and like that, and like that. Okay, so make those T's and then just bring down your verticals. And so there's your rectangle, and that line in the middle is just showing, indicating where we are going to assess the height of this at the middle of the rectangle instead of on the left or on the right. So hopefully you can see that those rectangles are a little bit more of a tighter fit. So this is going to be a better approximation. They look a little bit better, closer fit than here and a closer fit than here. So this is going to be a better approximation. The bummer with the midpoints is you have to go in and generate points. Again, you can't just use those points from the original, that 0, 2, 1, 3, 3, 6, was it 3, 6? No, anyway. We can't use all of those original ones. We have to generate some new ones. 1 over 2, 3 over 2. No, it's 2, 6. It was 0, 2, 1, 3, 2, 6, 3, 11, 4, 18. Yeah, we can't use those. We have to generate new ones. All right, so here we go. So we're going to square that. That's going to be 2 plus a fourth, 2 and a fourth. So this will be 9 over 4. Okay, so that's our first point, 9 over 4. Let me put my notes out here so I don't miss any of this computation. So this will be 2 plus 9 over 4, so 17 over 4. This will be 2 plus 25 over 4, so that's 33 over 4. And this is 2 plus 49 over 4. So we get 57 over 4 here. Okay, so those are the heights we're going to use. So we'll go in here, and because we're creating rectangles from the midpoint of the subinterval, this is called the midpoint rectangular approximation method, or MRAM. The height of each rectangle is the height of the function evaluated at the midpoints. All right, so the sum of all these rectangles, since these are regular subintervals, I can put this 1 here. We can factor out that width. Because these are regular subintervals, we have a width of 1. Okay, so the first height is 9 over 4. The next one is 17 over 4, 33 over 4, and 57 over 4. So all of that adds up to be 116 over 4, or 29 feet. So the elephant traveled approximately 29 feet in 4 seconds. So you can see that 29 is pretty close to the actual 29.33, assuming initial position of 0, and it's also pretty close to the add the left and the right up and divide by 2. Okay, so MRAM appears to be the best, but as the number of subintervals increases, all three of these sums, all three of these method will approach the same number. So we're going to push the subintervals to infinity, meaning we're going to push the change in dx to 0. We're going to use a limit to do that. And any one of the methods, once you put that limit on there, will produce the same result. All right, so here we go. Another question, just to kind of review, do a summary here. You're walking on the bank of a tidal river. There's a bottle. The tide's here in a bottle. The table shows the velocity of the flow every 5 minutes for 30 minutes. About how far upstream does the bottle travel during that half hour. Find the LRAM, RRAM estimates by using 6 subintervals of length 5. So if I'm going to do 6 subintervals with an L or an R, I need 7 data points, 1, 2, 3, 4, 5, 6, 7. Perfect, because L is going to use the first 6, and R is going to use the last 6. So you don't look at this one for the R, and you don't look at this one for the L. So at subintervals, that's awesome. 30 divided by 6 subintervals is 5, and these are already marked in 5, so this is an easy problem. So if you were on a time crunch on a test, you would say 5, and the LRAM, you're just going to grab these values. 1 plus 1.2 plus 1.7 plus 2.0 plus 1.8 plus 1.6. So the approximation here, this comes out, take your calculator, you get 9.3 when you add all of those up, and multiply it 46.5 meters. Okay, so that would be, if you were in a time crunch, just jam through it. It's never a bad idea to practice graphing, so just looking at this, we would just graph 0, 1, 5, 1.2, 10 is 1.7, 15 is 2, 20 is 1.8, 25 is 1.6, and 30 about 1.4. So we've got this kind of curve, this bottle velocity going like that. Bring that down, draw your vertical strips. All right, and we're going to start at the left for the LRAM and go over, complete the rectangle. 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 So some of these are inscribed and some of them are circumscribed. Just depends on the function, increase, decrease, concavity, that kind of stuff. All right, so not a bad fit. Looks all right. So there's your LRAM. Your RRAM, same 5 here, but now we're going to use these values. Not these. I probably shouldn't write it up there because we're not going to use the X values. I'll just erase these. And we're going to use these here. Okay, we're going to not look at the leftmost height. So this is going to be 1.2 plus 1.7 plus 2.0 plus 1.8 plus 1.6 plus 1.4. Okay, and that is 5 times 9.7, which is 48.5 meters. Okay. So the bottle will travel somewhere between 46, these are just approximations, and sometimes that's all you need is an approximation. And that's for during that 30 minutes. Okay, so let's graph it out so you can see the difference. 1.2, 1.7, here, 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 and here. All right, and so here we're going to, again, you get these verticals, strips at the right endpoint, and push left, push left, push left, push left, push left, push left, push left. Okay, so now these are circumscribed, and these are inscribed. There you go. Okay, so there's a review of LRAM and RRAM. So now I want you to try to do these. I'm going to pause the video and have you guys try these on your own. Take about 10 minutes and compute your LRAM, compute your RRAM, draw your graphs, compute your LRAM, compute your RRAM, and draw your graphs, and we'll see how you do. Okay, so now it's time for you to check your work. Let's see how you did. So hopefully, you can pause if you need to check, but hopefully your graphs look something like this. Notice the LRAM here, we have subintervals of 0.5, and these are just those 1, 2, 3, 4, 5, 6 values. So 34.7, and then over here, 1, 2, 3, 4, 5, 6 values with that width of 0.5. So somewhere between 34.7 and 44.8. So a lot of leftover, a lot of gaps here and a lot of excess here. So the velocity graph is increasing and concave down. Notice that the LRAM is less than the actual area and the RM is greater. So there's that one. And this one here, notice the velocity graph is decreasing with concave up, so the LRAM now is greater and the RM is less. So hopefully your graphs look like this. This was computed out to be, the first 10 hours, 70 and 63.2. So somewhere between 70 and 63.2. All right, so that's where we got to in class today, and we'll look forward to seeing you in class for 6.2 coming next. All right, bye guys.